Continuous stirred tank reactors are likely to be one of the most common reactor types that people in introductory chemical engineering classes will talk about and use. And CSTRs in practice are used for processing incredible amounts and quantities of solutions. An example of one would be waste sewage treatment plants, in which the residence times of molecules and within the reactor will be days or weeks. So CSTRs they can be incredibly huge things, and they are pretty exciting to talk about. They're probably one of the most talked about reactor types. So commonly what they'll be drawn as in process flow diagrams is these cylinders. And within these cylinders, we will have an inlet flow rate and an outlet flow rate. The inlet flow rate, the inlet molar flow rate is called FA naught, and the outlet flow rate is FA. And within the CSTR, we'll have some kind of solution and a propeller. The propeller refers to this stirred part. And by being stirred, what that means is that everywhere inside the CSTR, we are at some concentration Ca. And at this point, it's very important to note that with CSTRs, the outlet concentration is the same as the internal concentration of the reactor. The inlet stream is going to be a different concentration, Ca naught. And it's a very important distinction to note that the outlet concentration is the same as the internal concentration within the CSTR. And the CSTR will be usually some fixed volume V, and it has some concentration Ca. And so what I'm going to do is derive the generic mole balance for a CSTR. And the reason we would want to do this is so that we can have an idea of the interplay between the desired conversion, X, the volume, and the flow rates and the residence time. So to do that, we start off with a mole balance. So accumulation is equal to in minus out plus generation. And typically we'll assume that CSTRs are operating at steady state. Consequently, accumulation is equal to 0. The inlet term would be FA naught, moles of A coming in per time. And then we have an outlet term minus FA, and then we have a generation term plus RA times V, where A is your reactant, RA tells us the rate that A reacts per volume per time, and V is, we need to multiply by V to get the units to agree, because this mole balance equation has units of moles of A per time. The next step that we will do in our CSTR mole balance is, going back to Stoich tables, recognize that FA is equal to FA naught times 1 minus X. And X tells us the conversion. And intuitively, this should make sense, because if we had no conversion, if there was no reaction occurring in our reactor, X would equal 0. FA would equal FA naught, which is what we would expect because there's no reaction occurring. And then the other extreme is when X is equal to 1, when 100% of the reactant A becomes B or some other product, we would expect to have no A in our outlet stream. And in that case, we would have FA naught times 0, which equals 0, which is what we intuitively expect to happen with 100% conversion. So understanding this relationship is key. And a good review would be doing Stoich tables. The next thing we're going to do is expand this slightly, and we're going to say that FA naught, FA is equal to FA naught minus FA naught X, and then we're going to plug this into our mole balance above. And when we do that, we're going to have 0 is equal to FA naught minus FA naught plus FA naught X, so it's a double negative, and then plus RA times the volume of our CSTR. And we will see that these FAs cancel out, and what we are left with is 0 is equal to FA naught times X plus RA times the volume of our CSTR. And simplifying this expression, or rearranging it algebraically, we see that FA naught times X is equal to minus RA times the volume. So this is a very good place to be able to get to with CSTRs. We see the relationship between the rate of reaction, the desired conversion, the required volume, and the inlet flow rate. And if we assume that we are working entirely with liquid, in which case there will be no volumetric flow change. So if we decompose what FA naught is, FA naught is equal to CA naught times the V naught, where V naught is the volumetric flow rate, CA naught is the inlet concentration. That must be equal to the molar inlet flow rate of your reactant A, and FA would be equal to CA, the concentration of A in the reactor as well as the outlet stream, times the outlet volumetric flow rate. If we're working with liquids, we know that V is equal to V naught. And when we know that, we can define the relationship CA is equal to CA naught times 1 minus X. And we go to the definition of FA naught. So expanding the definition of FA naught tells us that FA naught times X must be equal to CA naught times V naught times X, and this is equal to minus RA times V. What we see, if we divide both sides of the equation by the volumetric flow rate, or V naught, so you can use V or V naught interchangeably because we're working with liquids. This term that we have here, I'll circle it, this is our residence time, and we call it tau. And if we look at the dimensions of tau, so I'll finish simplifying this and rewrite it in terms of tau first, and then discuss the residence time. What we see is that we have CA naught times X is equal to minus RA times tau. And tau will have units of, so tau is defined to be the volume of a reactor, we'll call it liters, divided by the volumetric flow rate, liters per second, which will have units of seconds. And so tau is a very important variable for chemical engineers to work with because it tells us the average time a molecule will spend in a reactor. And this final relationship that we reached, telling us that CA naught, the initial or the inlet concentration of A times our conversion, is equal to the rate of reaction times our residence time, is another very good relationship to understand about CSTRs, because we see the relationship we have here that tells us if we want to have a higher conversion, we must increase our residence time or have a faster rate of reaction. So this is a very good conceptual example of how these variables are related to each other. So if we wanted to increase the rate of reaction, we could do that by increasing the temperature. If we wanted to increase our residence time, we could do that by lowering the volumetric flow rate and or increasing the volume of our reactor. And doing both of these or either of these would cause us to have a higher conversion. So I hope you guys find this video useful. Let me know if you have any questions on CSTRs, and thank you for watching.